Guys, welcome back to TechDose, and in this video we will look at find building where Alice and Bob can meet. This is from Leetcode number 2940. The main aim of this video is to make you learn some advanced techniques so that you can solve some harder problems as well. So I'll be using the segment tree. Therefore, the prerequisite before watching this is to watch my entire playlist on segment tree. So I've already made a detailed video on segment tree explaining the construction and with the code implementation as well, and I have already made a video on range mean query. So I'll be posting all these links in the description below and also in the I button. You can just check it out. So from here on onwards, I will assume that you know everything about segment tree, right? Now let's look at the problem statement. In this problem, you are given a zero indexed array heights of positive integers where heights at I represents the height of the ith building. If a person is in building I, they can move to any other building j if and only if I is less than j and heights at I is less than heights at j. You are also given another array queries where queries at I equals ai comma bi. On the ith query, Alice is in building ai while Bob is in building bi. Return an array answer where answer at I is the index of the leftmost building where Alice and Bob can meet on the ith query. If Alice and Bob cannot move to a common building on query I, set answer at I to -1. So we will be looking at the example, but before that, let's look at the constraint. In this case, the heights array size can be maximum 5 times of 4 or 10 to the power of 4, and each of the values of heights can be in the integer range, and the queries can be maximum 5 times of 10 to the power of 4. So if you solve each of the query in, let's say, order of n time, then the entire time complexity can get qn, and if you multiply them together, then they will be 25 times or 2.5 times of 10 to the power of 9, which is greater than 10 to the power of 8. So you cannot solve each of the query in linear time. Therefore, a simplistic approach using monotonic stack will not work here. If you modify the approach, then it will definitely work. Otherwise, you can go for segment tree approach as well. Each of the queries will be in the format of ai comma bi, and they will be in the range of the indices of the heights array. Now let's look at an example for better understanding. In this case, let's say that we are given 6 items and we are given a bunch of queries. Our goal is to find the leftmost building where Alice and Bob can meet. Okay, and the constraints are only left to right move is allowed for both Alice and Bob, and a move from I to j can be made if I is on the left hand side of j, that means I is less than j, and the height at j must be strictly greater than the height at I. Okay, so these are the two constraints following which both Alice and Bob can make their move. Okay, now let's look at how the queries are solved. So if we apply a simplistic approach, and if I say that Alice is at 0 and let's assume Bob is at 1, then where they can meet? If they are at 0 comma 1, can they meet at 0? I mean, it is not possible because Bob cannot move to the left hand side. It is not allowed. All the movements to the right is allowed. Okay, so either Alice can come to Bob's home or they can meet at some index in future, that means on the right hand side. So can Alice come to Bob? Actually no, because the value at Bob must have been larger than the value at Alice, right? It should have been greater than 6, but it is already 4, which is less than equals to 6, right? So Alice cannot make a move to Bob. But then if you think about this 8, then Bob can move to this 8 because 8 is larger than 4 and also to the right hand side of 4. Also you can check it out with Alice. 8 is larger than 6 and also to the right hand side of 6. So we can make a move here, isn't it? And we can also make a move at index 5 too. So both Alice and Bob can also decide that we will meet at index 5. So there can be multiple options, but the problem requires you to find the earliest point of meeting. That means the leftmost point of meeting, and hence in this case the answer will be 2, because you cannot get an answer which is even to the left hand side of this index 2, right? So I hope you have understood how the queries are solved. Similarly for the 0 3, if Alice is at 0 and Bob is at 3, then their earliest point of meeting will be 5, because they cannot meet at 4 and they cannot meet at 3. Why they cannot meet at 3? Because the value 5 is actually less than equals to 6, and for the same reason they cannot meet at 4 as well. But at 5, 7 is actually greater than 5 and 6, and it is to the right hand side and it is the leftmost index, right? So that is why the answer will be 5. If you look at this 2 comma 4, if Alice was at 2 and Bob was at 4, then can Alice come and join Bob at its place? No, because this 2 is actually less than equals to it, so it will not be possible. And if you look at the right hand side items, there is only one item 7. So yes, Bob can move to this 5, but then Alice cannot move to 5 because 7 is less than equals to it. So in this case, meeting is not possible. Therefore, we will be writing -1. For this 3 comma 4, you can check out that they can meet at index 5. So we will be writing 5. Now for the case of 2 comma 2, both Alice and Bob are at 2 at the same spot, and therefore no movement is required, and we can output the answer 2. They have already met. Okay, so we have to just pack this into an array and send it as a resultant array, right? So if we do each of the queries in linear time, then you know that the time complexity will be NQ, which will take 2.5 times of 10 to the power 9 operations according to the constraints given, and therefore this will definitely give you a time limit exceeded, right? So we want to solve each of the query in at least logarithmic time or O1 if possible. I mean, we have to do something better than linear time. So if you have understood this example carefully, then you have already understood that this problem is all about finding the next greater element in a given range, like what we were doing for this 0 comma 3. If you carefully understand, when Alice was at 0 and let's say Bob was at 3, then what we were doing, first of all, we were finding if Alice can come and meet Bob at its index, and if it was not possible, then what we were doing in the rest of the segment, that means in the suffix of the array starting from this Bob's place plus 1 till the end of the array, we were finding, just take the maximum of these two values, which will be 6, find the next greater element of 6. Simply find out the index of the next greater element of 6. So what is the next greater element of 6? It is 7 and its index is 5, and that is how we have entered 5 here. Okay, now if you look at what we were doing for this 3 comma 4, so for this 3 comma 4 as well, since Alice cannot come to Bob's place because 2 is actually less than equals to 5, therefore we were trying to find the next greater element of 5. Why 5? Because among this value of Alice and Bob, 5 will be maximum, and so its answer will be 7, and the index of 7 is 5. Therefore we were saving 5 here. Okay, so this problem is all about, given the index of Alice as I and the index of Bob as j, where I will assume that I is less than j, then the problem says that find the next greater element of the maximum of Alice and Bob. Okay, we don't want to exactly find the element, but find the index of that element, right? So I hope you have got the crux of this entire problem. So this problem is about finding the next greater item in the given range. Now let's understand how we can actually make it happen. So let's say that our query type will be next greater element of a given value in the range of L to R. And let's say that our value is 2. Okay, and I want to find the next greater element of 2 in the range of 3 to 7. How can we make this happen? Now I can also rewrite this query according to the problem statement as if Alice value was 1 and the Bob's value was 2. That means Alice is at index 1 and Bob is at index 2. Now can Alice come over to Bob's place? No, because this 1 is actually less than equals to 2. If this Bob's value was actually greater than 2, then Alice can meet at Bob's place. Okay, but in this case it is not true, and when it is not true, then both Alice and Bob will have to move to some future index, that means on the right hand side, and they have to meet there. And how to decide which point it will be? It will be decided by the maximum of these two values, 2 comma 1, and definitely it will be 2. And I also want the leftmost value to be the result, isn't it? So I will be finding out the next greater element, which will give me the nearest item to the right hand side, which is greater than this 2. Okay, and I want the index of it. So I hope you have understood our requirement. Okay, so find out the next greater element of 2 in the range of 3 to 7. If you happen to solve this problem, then you can just do a linear search over this range, and as soon as you find an item which is greater than 2, you will stop and you will return its index as an answer. And that is absolutely correct, isn't it? But in the worst case, for solving this, you may require to do a linear search over the entire array itself, and therefore each of the query will require order of n time of traversal. Therefore, for all the queries you will require q n time, and we already know that it will exceed our time limit. Therefore, we cannot afford a linear search here. Okay, so linear search is not a good idea. In this particular case, you can actually apply binary search. You might not understand why we are applying binary search here, but you will understand it in a little while. So stay with us. In this case, what we will do is we will be applying binary search. So our low value will be equals to the start range, and our high value will be equals to, let's say, 7. Okay. Now in this particular range, I will be finding the mid, right? What will be mid? Low plus high minus low by 2. So this will be equals to 3 plus 7 minus 3, 4 by 2 is 2. So this will be 5. So if this value is low and this is high, then you know that the mid value is 5. I will be finding out the maximum in this range from L to M. And let's say I can get the maximum in log order using segment tree range max query. If you build a segment tree for querying the range max, then you can always get the range max query in the range of L to R in order of log n time, where n is the size of this entire array. Okay, so we will see this later, but let's say that this is something which we can get in log n time. So what is the maximum in this case? It is 5. So I will implement the segment tree in such a way that it will always return the index. So the index 4 will be returned. Okay. Now what item I was searching for? I was searching for something greater than 2, and I found at index 4 I found a item which is greater than 2, isn't it? So I will save it in our answer. So my answer will be 4 now. Okay, it was initially infinity and I will update it to 4. Fine. So since I could find a next greater item in the first part from low to mid, then I don't need to search in this area. I can do further search only on the left hand side. So I will update my high to mid minus 1. Okay, and I will reduce my search area from low to high, and then I will again recalculate the mid, and the mid will be equals to low. In this case, again, if you check from low to mid, then the value here is 3, which is greater than 2. So the range max query which returned index 3, having said that 3 is the maximum in the range of 3 to 3, is actually greater than 2, and therefore since this 3 has a lower index value, so I will update this to 3. And now I will update my high to low minus 1. So since high is smaller than low, so I will stop, and my answer is saying that the leftmost index where I found the value greater than 2 is actually index 3. Okay, so I can say the next greater element index of 2 will be equals to 3. At index 3 I found the next greater element of 2. So this is how I will be calculating, right? So the answer in this case will be 3. This is the index, not the value. Now if I can show you another dry run on some other example, then let's say that I will be taking this 4 to 7. So this means that in the range of 2 to 7, I want to find out the next greater element of this 4. And this query can be rewritten in terms of our problem as if Alice was assigned this index 0 and Bob was assigned this index 1. Then can Alice go to Bob's place? No, because this 2 is less than equals to 4. So they both have to meet some point on the right hand side. So it has to be the next greater element of the maximum of these two numbers, which will be 4. So I need to find that out. Okay. So how to find? Let's say the low value is here at 2 and the high value is at 7, right? Now I will find the mid value. So the mid value will come out to be at index number 4. Okay. Now I will be finding the range max in the range of 2 to 4. I can use the segment tree to do that, and the segment tree will say that index number 4 has the max value, and index number 4 is saying that I have a value of 5. Okay. So since my answer will be initially infinity, and since this index 4 has a value 5 which is larger than 4, so I'll be updating this to 4. Okay. Now since I found an answer in the range of low to mid, and since I always want to find answer on the leftmost item, Therefore I will remove this search range by updating high equals to mid minus 1, and I will be searching in this area. If you continue to search in this area, you will never find definitely an item which is greater than 4. So it will ultimately stop and we will end up with an answer 4. So here the answer will be equals to index number 4. Okay. So I hope you have understood the idea of using segment tree with binary search. If you use binary search for each query, then the total time complexity will be q times of log n. Now q can be 5 times of 10 to the power of 4, and log n time will be somewhere maximum 20. So you can expect that it will be 10 to the power of 6, which is way below your 10 to the power of 8. And definitely this is going to run within 1 second. Now let's recap some points about the segment tree. Now segment tree is a balanced binary tree, therefore its height is guaranteed to be log n order. It is implemented by using 1D array, the simple segment tree, and the size of the array will be 2 to the power of height, or you can also take 4n size. If you want to see the proof of 4n, you can follow cpalgorithms.com and you will find the proof of this. Okay. Now in one indexed implementation, which I had already shown in my construction video of segment tree, if your root index is, let's say, I, root means any current node index, if it is I, then its left child will be at 2i and the right child will be at 2i plus 1, and its parent will be at I by 2. I had also explained in the segment tree construction about the 3 cases of overlap. So a no overlap case will happen when you are asking from query start to query end, QS and QE is what you are asking, and S and E is what the node is holding. Okay, so let's say you are asking for a range max in the range of 0 to 2, but the current node of the segment tree is saying that I have the range max in the range of 4 to 6. So this is not useful because there is no intersection. Okay, so in such cases I will just return back without returning any answer, right? Now we have the second case as total overlap case. In this case, you are asking, let's say, the range max in the range of 0 to 6, and you are getting range max in the range of 3 to 4. So 3 to 4 is something you need, but you need even more, right? So you will take this answer and you will search elsewhere too. Okay, so this will be returning whatever is stored at the node value. So this will also return. Now in case of the partial overlap, you can see that if you are asking from QS to QE, but there is some part in intersection, but some is unwanted part. Okay, so in this case, if you are asking range max in the range of 0 to 3 and it is giving you range max in the range of 2 to 5, then some part is needed, 2 to 3 is needed, but then 4 to 5 is not needed for you, right? So in this case, we will do further left and right branch calls. Okay, now at any particular node, there will be either of these 3 cases: no overlap, total overlap, or partial overlap, right? So if you are considering no overlap and total overlap, it will immediately return and there will be no recursion call. But if you consider partial overlap, then there will be left call, right call, and then we will be further exploring. The endpoints of the line segment actually creates partial overlap. So since a range can have exactly 2 endpoints, not more than 2 endpoints, therefore there can be maximum of 2 partial overlap, and therefore if you draw a tree, then there will be maximum 2 root to leaf path, and you know that the height order is log n, therefore the time complexity will be 2 times of log n at max. Okay, so this proof was also shown in, I think, the construction video. So I hope you have already understood that. Now let's try to build the segment tree. Let's say that our given array is having 6 items. Then I'll be using an approach similar to binary partition of merge sort, and I will be trying to divide this into 2 parts. So I'll be starting with the low value of 0 and let's say the high value of 5. Okay, or you can say that the start value of 0 and the end value of 5, whatever is the case. So I can simply make 6, 4, 8 on the left side and 5, 2, 7 on the right side, and I can write down the same indices as it is shown. Okay, and I can easily divide it. Now if we have odd number of items, then I will take one extra item on the left hand side. This is my idea. Okay, so I am completely dividing all the array items, and you can see I am marking all the indices. Okay, fine. Now we can also further divide these items into singular items, and I have already divided them. Okay, now I can mark the indices as 0, 1, 2, 3, 4 and 5. Now if you imagine about how it will look in the node structure, then I can make a binary tree like structure on the right hand side, and it will be completely depicting what you are seeing on the left hand side. Okay, so this will be the structure of the binary tree. Fine. Now if you consider the start and end value, then the start and end value is 0 to 5 in the initial case, and if I divide it in the middle, then on the left hand side we have the range from 0 to 2. On the right hand side we have a range from 0 to 5, 3 to 5, right? On the left hand side you have a range from 0 to 1, and this is 2 to 2. This range is from 3 to 4, and this is from 5 to 5. This range is 0 to 0, this is 1 to 1, this is 3 to 3, and this is 4 to 4. This is how you can actually divide the segment tree, isn't it? So this structure is your segment tree. We will call it seg tree. Now in this segment tree, when you divide, the leaf node is the node which will be storing the array item. So let's store the array items. At 0 0 means whatever we have at 0 you just store it. At 1 1 means whatever you have at 1 you store it. Similarly 8 will be here, 5 will be here, 2 and 7. Now since we are solving this problem not based on the items but based on the index, therefore I will not write the values but I will write the index. So this will be 0, this will be 1, this will be 2, 3, 4 and 5. If it was the range sum query or something else, if index was not required, I will write the values. But in this particular problem, I am interested in index. So that is why I am overwriting it with index. Okay. So index will be present. Now what will be the internal node? Since it is a range max query, that means if 0 to 1 is given, then this particular node will be storing the index of the item which is maximum in the range of 0 to 1. So you check out whatever is the maximum on the left side, which is 0, it is having a value 6, and whatever is the maximum on the right hand side, which is 1, which is having a value 4. Out of these two values, 6 is larger, so its index will be saved here, saying that in the range of 0 to 1, index number 0 has the maximum value. And on similar note, you can check out that at 0 to 2, you will be storing whatever is the maximum between this 0 and 2. So 0 has 6 value, 2 has 8 value. So here 2 will be stored. Okay, on the right hand side, compare between 3 and 4. So 3 will be here because 5 is greater than 2. Between this 3 and 5, you check out 5 will be stored. Between this 2 and 5, 2 will be stored because 8 is larger, right? So this will be your entire segment tree construction. Now if you imagine about how the array implementation will be done, I had already explained in the construction video that I will be doing, let's say, 1 based indexing, and similarly I will just be taking a 4n size of the array, or you can also do it based on the height. So let me write a few items here, 13, 14, 15 and so on, 16. So I will be assigning the index value. So this will be at index 1, and according to the previous ideas that we have seen, the left child will be at 2i, the right child will be at 2i plus 1. So the left child will be at 2 times of 1, 2 times of 2, 2 times of 4. Okay. Now this will be at 2i plus 1, 9. This will be at 5, 2i plus 1. This will be at 2i plus 1, 3. This will be at 6, 7, 12, 13. So if this is your array, I think now you can easily fill out what will be the array items. Okay. So if I just briefly fill these items, here you will have 2, 2, 5, 0. Then you will have 2, 3, 5, 0, 1. And then this 10th and 11th entries will be empty because these are the left and right child of this index number 5 which are not present. For this 12 we have 3, for this 13 we have 4, and all these will be empty. So this will be your one-dimensional segment tree array implementation. So I hope you have understood this. Once you have built, your segment tree will look something like this. Okay, so I have pre-made this entire thing. Let me now show you how the range max query works on this entire segment tree. So let's take the first query. That means I want to find out the range max in the range of 1 to 3. So if you look at this array, I am querying about what is the maximum number in the range of index 1 to 3. I want to get this value 2. I want to get the index of the maximum number in the given range. Okay. So this entire segment tree actually stores the index, as I already told you. Now since I want in the range of 1 to 3, my QS query start and query end will be 1, 3. So I want to search in the range of 1, 3, and I am getting the information in the range of 0 to 5. So we have a partial overlap in this case because 1 to 3 is something I want and 0 to 5 is something I'm getting. So I'm getting more than what I want. So definitely I have to clean up the item from 0 to 0 and 4 to 5. So I'll be making two calls both on the left and the right side. On the left side, if you see here, I want in the range of 1 to 3 and this node is giving me in the range of 0 to 2. So this is also a partial overlap case. Then I'll be making calls on both the side. If you look on the left side 0 to 1, then this is also a partial overlap case because I want from 1 to 3. So there is some intersection, but there is something which is outside of our need. Okay, 0 to 0 is outside. So again a partial overlap case. I'll be moving to both left and right. If you look at this 0 to 0, I want from 1 to 3. So there is no intersection. So this is a no overlap case. And in this case, I can return minus infinity or something, which I don't want to see. Okay. On the right hand side, you can see that we are getting information from 1 to 1 and we want from 1 to 3. So if you look at the previous three cases which I had explained, it is a total overlap case. Okay. So in this case, I will be returning the value 1. So from here, I will be returning a value 1 because this minus infinity is invalid. So I'll be returning a value 1. Okay. Now since I got a value 1 at this node, then I'll be going to the right call, and here I want information from 1 to 3 and I'm getting information from 2 to 2. So everything is what I want. I may want something more. So I'll be getting a value 2. Now when I receive two values, one from the left side and two from the right side, I will be comparing at index 1 and 2, which index is having the larger value. So index 2 is having 8, which is larger. So this will be returning the maximum of the value stored at index 1, 2. So this will be returning the index 2. On the right hand side, I want the information from 1 to 3. This is giving me 3 to 5. So there is something in intersection, but something which I don't need, which is from 4 to 5. So this is partial overlap. I'll be making two calls left and right. On the left side, again, this is partial overlap. I'll be making two calls left and right. At this point, I want everything. That means 3 to 3 is definitely wanted, but I want something more as well. So I will be returning this value 3 from here. If you look at this point, I want from 1 to 3. This is giving me 4 to 4. So I will return minus infinity from here, which is an invalid value. So at this point, one value is invalid. So I'll be returning 3. Okay. So 3 will be returned from here. Now on the right hand side, I want from 1 to 3. This is giving me 5 to 5. So no overlap case. And this will be returning minus infinity. So since this is minus infinity, the 3 will be returned from here. Now at this particular point at the root node, what this will return is it will check these two are valid values. So we have to check which one is the larger value. So we will see that 8 is larger than 5. Therefore index 2 will be returned. Okay. So the range max query of this will be returning index 2 as an answer, right? In 1 to 3, index 2 is holding the maximum value. If I again do a dry run on this range max query in the range of 2 to 5, you can check out that in the range of 2 to 5, you should again get an answer 2. But let's try to do it. In this case, we will start at the root node again. And I want from 2 to 5, this is giving me 0 to 5. So this is a partial overlap because 0 to 1 is something unwanted. We have to do cleanup. So I'll be making calls on both left and right. On the left hand side, we are getting information from 0 to 2. I want from 2 to 5. So this is again partial overlap. Make two calls left and right. On the left call, we want from 2 to 5 and this is giving me 0 to 1. So no overlap, return minus infinity. On the right side, we are getting 2 to 2. We want 2 to 5. So we will be returning the entire index 2. So since one of the index returned is invalid, so I'll be simply returning this 2. Okay. And here on the right call, I want from 2 to 5 and this is giving me 3 to 5. This is a total overlap case because everything is in intersection. So I'll be sending 5 here. Now this root node will be returning the maximum stored at index 2 and index 5. Just compare. At index 2 we are storing 8. At index 5 we are storing 7. So which one is larger? 8 is larger. So return its index. So 2 will be returned and again you will get 2 as an answer. So I hope you have understood how the range max query is done on the segment tree. So let's now look at the dry run using the binary search along with the segment tree range max query. Now once you have made the segment tree, then let's try to apply our binary search with the segment tree RMQ, that means the range max query technique. Okay. Now in this case, let's say the array is having 6 items and I'm trying to do the query 0, 1. This means that let's assume Alice is at 0 and Bob is at 1. Now you must be careful that Alice can be given, let's say, value 1 and Bob can be given a value 0. So in the code, I will make a swap in such a way that Alice will always be holding the smaller index and Bob will always be holding the larger index. So if this is the input, then I will swap the values. Okay. So let's assume that it is already there, like Alice is having a lower index, at least in index less than equals to Bob. So first thing I will check is if Alice's index is same as Bob, then I don't need to do any binary search, any segment tree RMQ, nothing is required because they are already present at the same place. Then in such a scenario, I don't need to solve it, isn't it? So if I give you a query that 2, 2, then in such a case you can simply return an answer 2 because they are already present at the same index. Or if I give you an index, let's say 1, 2, then in that case Alice is to the left hand side of Bob. Okay, that is fine, but the heights at Bob is actually larger than the heights at Alice. Okay, you can check it out. The heights at Alice is 4 and the heights at Bob is 8. So Alice can go and hang out with Bob at its index. And in such a case, when the height of Bob is actually larger, then I can simply return the index of Bob because Bob don't need to move anywhere, isn't it? So these two checks I have to do initially before having to apply the binary search and segment tree. Okay, so let's say that I'm taking such a query where I will be requiring to do the operations. Okay, so I'm trying to find out if Alice is at 0 and Bob is at 1. So Alice is at 0 and Bob is at 1. Then how to solve this problem? So in this particular case, you will have to find the next greater element of the maximum of this 6, 4, which will be 6. Okay, and you want to find the leftmost index. That is why I'm saying next greater element. So in the range of this 2 to 5. Now let's assume, I can assume the low value to be at the Bob's place or at the Bob plus 1's place, whatever place you want to do it, you can just take it. And simply you have to find the mid item. So let's say this is the mid value. Now since I am finding the next greater element of 6, so I'll be finding the RMQ value. That means the range max query in the given range. Let's say that I started at this index 2 and now you are required to find the RMQ in the range of 2, 3, and that will be giving me an index 2. Okay, so this is giving me an index 2. So I found an answer in the range of low to mid. Okay, so since I found an answer, I don't need to solve for mid plus 1 to high because I am interested in the nearest item and I already found a candidate. So my answer will be updated to index 2. Now what will happen is my high will become mid minus 1 and the low is also at 2. Mid will also be the same. If you do a range max query in the range of 2 to 2, again you will get 2. Okay, so 2 is already stored in the answer. Okay, it is fine. This value 8 is already greater than 6. We already know that, right? So I'll be moving my high to left side of the low, and since high is less than low, therefore I have to stop my binary search, and the answer in this case will be index 2. Now let's look at the next query 0, 2. In case of 0, 2, you can check out that since Bob is having a value larger than Alice, therefore Alice can come and hang out with Bob. So the answer in this case will be 2. This is hitting our base case as well, right? So this is how you can solve the entire problem using binary search and segment tree RMQ. Again, I am repeating our idea that in this particular case, if you had already decided that I am applying binary search in the range of L to R and I found a mid value, and let's say I was finding out the next greater element for this value 8, and let's say that in this case the RMQ actually gave me an index of, let's say, 5, and the heights at 5 turned out to be equals to 7. This means that there is no item from low to mid which is actually greater than 8, and therefore we will not be searching in this range, and my low will be updated to mid plus 1, and I will be searching in this range, and my mid will be updated here, right? Now in this case, if I again search in the range of low to mid and the RMQ value is giving me an index, let's say 10, and the height array at 10 is equals to, let's say, 12, then since this 12 is greater than 8, therefore I found a candidate for the NGE, that means next greater element, in this range of low to mid, and since I already want a leftmost item, therefore I will exclude this range from mid to right, and I will reduce my right value to mid minus 1. Okay, so this is my entire idea. I hope you are able to understand this binary search and segment tree RMQ technique. In this particular approach, the time complexity for construction of the segment tree with having 4n size of the array will be order of n, and the binary search time is log n, right? Because the size of the array is n, and we are solving for each of the query. We have to apply binary search and also the range max query. So all of these will be multiplied together, and therefore you can say that the time complexity will be order of n plus q times of log n square. Okay, and the space complexity will be order of n for the segment tree, and for the recursion call stack for the segment tree it will be log n, because you know that the height of the segment tree is log n. And the queries, since you have q number of queries, therefore you can say that storing the answer will require extra space of q. But if you don't consider the answer to be extra space, then the extra space will be order of n. Otherwise you can also answer n plus q. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the heights array and the queries array. So I'll be finding what is the size of the heights array and storing it in n. And then I will be initializing my segment tree array, which will be of size 4n plus 1, because a segment tree cannot have more than 4n items at any point of time. And I already referred you for the proof to CP algorithms. I will be doing one based indexing of the segment tree. The root will be at index 1, so I am storing st index equals 1. Then I will be building the segment tree. So let's see the build code. Now if you look at the build segment tree code, I have already declared the segment tree as global inside the class, and this is the code for building the segment tree. I'll be getting the heights array with the start and end. Initially the start will be 0 and the end value will be n minus 1. The st index value will be 1 because the root node will be having index 1, right? And it will be storing the range max in the range of 0 to n minus 1. Okay, now if I am at the leaf node, that means start equals to end, then the segment tree will be storing the index of the array as I had shown you while doing the construction. Otherwise, if it is in an internal node, then we will be finding the middle point and dividing the entire range of L to R in the range of low to mid and mid plus 1 to R. That means here start to mid and mid plus 1 to end. Now having an index st index, if I want to go to the left hand side, it will be 2i and the right hand side will be 2i plus 1. So from the segment tree index, I will be going to 2 times of segment tree index on the left side and 2 times of segment tree index plus 1 on the right side. Once I am back, then I will be comparing the max value of both the left and the right child, and whichever one is larger, that index I will be storing here. So this is that comparison part, comparison and updation. Okay, so this is how we will be building the segment tree. And after building the segment tree, if I want to do certain kind of range query, let me show you the range query as well. So if you are given the heights array and the QSQE is the range max that you want, that means if you want the RMQ range max query in the range of 2 to 4, then the QS will be the query start point, QE will be the query end point. The start and end is actually the for a node, what is the range it is storing, that is start and end. And then the st index is the current segment tree index, which is implemented in the form of an array. Now this is the case of total overlap. In the total overlap, just return the value. In case of no overlap, I will be returning an invalid value, which is integer minimum or minus infinity. Otherwise, if there is a partial overlap, then I will be further making recursion call in both the parts. So if my range is from S to E, then I will be making a call from S to mid on the left side and mid plus 1 to high, that means end on the right hand side. And I will get both the left max and the right max, and I will check if the left max is integer minimum, that means minus infinity, that means I will be surely returning the right max. You can just think about it, right? And if the right max is returning integer minimum, then I will be returning the left max. Otherwise, if both of them are actually valid values, then I'll be comparing which one is the larger, and that one I will be returning simply. Okay, So I think you have understood the range max query as well. Since I have already referred you to my video on range min query, so the range max query is the same. Just the function needs to be changed from max to min. Now having done all this, having built the segment tree, let's now look at how to do the queries. So I'll be storing each of the query result into the result array, and I'll be going through each of the query. As I said that Alice will always be assigned the minimum index of the pair. So I'm maintaining that, and Bob will always be the right hand side index. Okay. Now these are the base cases. If Alice and Bob are at the same place, so no need to move. I will just store the index in the result. Otherwise, if the height of Bob being on the right hand side, Alice being on the left hand side, if the height of Bob is larger, then Alice can always move to Bob's place, and therefore I will just store the index of Bob. Okay. So if these base cases do not hit, then what I do is there must be a future item where both Bob and Alice has to move, and if both of them have to move, then this value x here must be larger than both the items. So I'll be taking the max of Alice and Bob, and I'll be finding the next greater element of this. Because why the next greater element? Because we need the leftmost item which is greater than both A and B. So that is always given by the next greater element. Okay, and we want to store the index of this x. So that is what we are doing with the binary search. So I'll be starting with Bob being the low and high will be the end of the array. Okay, so we are doing binary search on the suffix of the array, and I'll be taking the answer which will be initialized to infinity, which is showing invalid value. I'll be doing the binary search on the range. So if I apply binary search in the range of L to mid, like in this case low and high is present, so if I apply it on mid, and if I am finding the NGE of, let's say, a value 10, and if I do an RMQ here, I have to first do an RMQ in the range of L to mid. You can check it out. I am doing RMQ range max query in the range of low to mid, and if I am successfully getting a value, and let's say this value is coming out to be index 8, and this index 8 has a value 9, which is actually less than equals to 10. It is not greater than 10, right? That means in this range I cannot find any next greater item of 10. So it's better that I update this low to mid plus 1, and that is what I am doing in this else part. Okay. Otherwise, if I found an item which is actually larger than this 10, let's say it was 11 or something, or 12, then I will be further exploring in this. I will be storing the index of that in the answer, and I will be further exploring by moving my high to mid minus 1. I'll remove this range of mid plus 1 to high. So after doing this binary search, then I'll be checking if I did not find even one candidate, then I'll be saving -1 for the answer. Otherwise, I'll be saving the leftmost index of the given candidate. And finally, I will have to return the result after serving each of the queries. So I hope you were able to understand this entire solution. Yes, this solution may not have been easy to understand. A good understanding of segment tree as well as the range max query with binary search is very important. But as I said, that the aim of this video was to make you learn something advanced and something new. So if you still have any doubt, then feel free to comment below, and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of this programming videos. See you guys in the next video. Thank you.